Okay, let us consider another example. Example 2. We know that a linear system of order n can be represented as a system of n first-order linear ODE. So to illustrate the procedure once more, let us consider the system representation, okay, of the second-order ODE in our first example. In other words, okay, we convert the ODE in example 1 into a linear system of two first-order ODEs. Okay, so look, to convert it, letting for this, letting x1 y. Okay, we introduce a new function of t, which is y, and which is denoted by x1. And its derivative is defined as another variable, dependent variable, which is a function of t. Okay? With these two functions, we have, look at that, x1 prime, the derivative of x1 is y prime, which is x2. Good. We get a first equation. This is a first order ODE. Good. In two variables, x1 and x2. And the second equation is obtained from the differential equation itself. And look, from the differential equation, from the ODE itself, we have, look, y double prime in our equation is x2 prime. Good? Because y prime is x2, so y double prime is x2 prime. Plus, or minus, t over t minus 1, y prime, which is x2. Good? And plus 1 over t minus 1, y, and y is x1. And on the right-hand side, we have 1 over t minus 1. Therefore, this is a second equation which which is a first-order ODE because only the first derivative of x2 appears in this equation. Or solving for x2, or x2 prime, look, we get the second equation. x2 prime, yes, becomes 1 over, with a minus sign, minus 1 over t minus 1 x1 plus t over t minus 1 x2 plus the non-homogeneity term, 1 over t minus 1. So this is the system representation of our second order linear ODE, which contains two first order ODE in the unknowns x1 and x2. Look, in matrix form, so we have, look, with the vector function, remember, this tilde is used for a quantity which is vector or matrix, or x of t, so I consider the vector function with component functions, x1 and x2. I define this. Good. So our system takes the form. Our system may be written in matrix vector form as this. x1 prime, x2 prime. Good. Look at that. We have x1, x2. So first row entries suggest that x1 prime should be x2. So this matrix elements are 0 and 1 to imply the first equation, 0x1 plus 1x2. Good. X2 prime, the second equation, we have minus 1 over t minus 1 times x1. So this coefficient or this entry of the matrix, coefficient matrix must be 1 over t minus 1. And this and t over t minus 1 multiplied by x2 plus an additional term. So no non-homogeneity term for the first equation, but 1 over t minus 1 for the second equation. So which is precisely in which form, look, the derivative of vector function, which is the required solution, is a matrix times x self plus a non-homogeneity term. Good? Or this, recall, now this is the coefficient matrix A, and this is the matrix B of the vector valued function with components 0 and 1 over t minus 1. So our second order non-homogeneous linear ODE in the first example, or in example 1, is written as a first order non-homogeneous system of two equations where the vector, unknown vector function is a vector function with two component functions. Okay, explicitly we have this system. So then find the solution of the system or general solution of the system. Good. So please be careful. We already know that y is, we know that y of t, the general solution, is of this form. C1t, c to e to the power t plus 1 from example 1. And what is y? So now I'm looking for vector solution, x vector. So I have to find its two component functions. So this is nothing but x1, isn't it? Y is x1. So this is x1. Let's write it as, which is nothing but first component function from example 1. And its derivative, look, c1 plus c2 e to power t is nothing but x2. Good? So the required vector solution has the form. So the required vector solution, so vector solution x of t has the form c1 t plus c2 e to power t plus 1, c1 plus c2 e to power t. Okay? which may be written as C1 times T1, good, C2 times e to the power t, e to the power t, plus 1, 0. Correct? Actually, this vector is equal to the sum of these three vectors, C1t, C2 e to the power t plus 1, and so on. So this is the first vector solution. We sometimes denote by x1. This is the second vector solution of the corresponding homogeneous system. And this is nothing but a particular vector solution. A particular solution as a vector, 1, 0. Okay? Or in this form, look, T1 e to power t, e to power t, C1, C2, plus 1, 0. Good? Or this, where C of t, this matrix t e to power t1 e to power t is a fundamental matrix solution of the matrix equation C prime is a C, or its columns are linearly independent vector solutions of the homogeneous, corresponding homogeneous system. Actually, look, it is not difficult to see that the Wronski determinant of the fundamental matrix here, determinant of C is this, e to the power t, t, e to the power t1, e to the power t, good, which is t minus. Sure. Acaba ne zaman gitti? Okay, so finally, we see that the Wronski determinant of the fundamental matrix is non-zero, okay? Which is the case. This is non-zero for all t except t is equal to 1, which is very well known. So as you see, we say that the system representation, and there is a one-to-one correspondence between the system representation and this single second-order ODE, in the sense that if we find the solution of either the system or the linear higher-order ODE, we can find the solution of the system representation or vice versa. Actually, in this case, we use the known solution of the single ODE of the second order to find the solution of the first order system, right? Without any trouble. Okay, so we understand that the theory of the linear higher order equations is well established. So we know the basic structure of solutions without solving the linear ODE. To be specific, let us consider the second order ODE. second order linear ODE, which encounters frequently in practice. Actually, in practice, we often encounter a second order linear ODE, which has the form d squared y dt squared plus a1 of t dy dt plus a2 of t, y is b of t. Good? So it is known that the required general solution is of the form. So y of t is homogeneous solution plus a particular solution, or more explicitly, because this is a second order ODE, homogeneous solution is the linear combination of two linearly independent solutions. Good. So it is very well known that the solution we require is precisely in that form. So it is a combination of y1 and y2. Please be careful, where y1 and y2 are solutions, or of course linearly independent solutions of the corresponding homogeneous ODE and y of p is a particular solution. Satisfying the non-homogeneous ODE. So from a practical viewpoint, we have to find three functions, y1, y2, as linearly independent solutions of the corresponding homogeneous equation, and a particular solution which satisfies the non-homogeneous equation upon substitution. Okay? But unfortunately, there is no general method to find y1, y2, and yp. Good? Although the structure of the required solution is very well known from the theory of linear ODEs, there is no general method to determine explicitly all the three solutions which are necessary to form the general solution. And in fact, it is in general, it is not possible to express all the three solutions, even in the second order case, in terms of a finite combination of elementary functions of mathematical analysis. This is not the case. So let's write this as an important remark. Even for the second order, simplest second order case, in general, solution of the linear ODE is not expressible as a combination, in fact, as a finite combination, as a finite combination of known elementary functions of mathematical analysis. I mean, look, I'm repeating once again, I need to find y1, y2, y3. And I say that, in general, these three functions are not expressible as a finite combination of known elementary functions, such as exponentials, logarithms, trigonometric functions, or inverse trigonometric functions, or polynomials, or rational functions. This is not the case. Okay? The general solution is not expressible as a finite combination of elementary functions. In our previous example, okay, remember that the two solutions are nicely t, which is a monomial, and e to power t, which is an exponential function. So the two solutions are very well known. But in general, this is not the case. And you shouldn't think that you are going to express the solution. Even for the second order case, you are not going to express, it is not possible to express y1 as a finite combination of simple elementary functions. You may not express y2 as a finite combination of elementary functions. And this is true for yp as well, okay? But there is a specific linear ODE of order n whose all solutions are expressible as a combination of very well-known elementary functions, such as exponential functions, trigonometric functions, and monomials. Okay? That is the case where the linear differential equation has all constant coefficients. Okay? And we also show that whenever the solution of the homogeneous equation, okay, provided that the solution of the corresponding homogeneous equation for the second order case, y1 and y2 are both known, it is not difficult to find particular solution. In other words, it always true that, okay, it is true that we can always determine a particular solution whenever y1 and y2 are known. Okay? So it is of crucial importance to solve the homogeneous ODE, right? So let us now focus our attention to the linear homogeneous equations with constant coefficients. So linear homogeneous, our title is homogeneous ODEs with constant coefficients. So we consider this equation, yn plus a1 yn minus 1, a2, yn minus 2, an minus 1, y prime, any is 0, where a1, a2, an are all real numbers. Real numbers. Some specified or some definite real numbers, okay? Not functions of t. All of them are constants, real constant, and the non-homogeneity term on the right-hand side is 0, making the equation homogeneous. So in matrix form, in operator form, we have this equation. Ly equal to 0, where L is dn plus a1 dn minus 1 an minus 1 d plus an. Okay? So sometimes, now this differential operator is independent of t, isn't it? Look, the coefficients a1 up to an are some real numbers. So formally, you can view L as a function of d, the operator d, which is a polynomial of degree n. So sometimes L is regarded as a polynomial in D of degree n, written as L of D. Actually, look, formally, this is thinking that this is a 1 or D0, this term is identity operator or unit operator. And our equation our equation is written in this form. So homogeneous ODE with constant coefficients in operator form. So we write the homogeneous ODE in operator form like that. L, which is formally a function of D. Do not forget D is the derivative operator with respect to the independent variable. Okay? And here in this equation, Y, the required solution or the dependent variable is some function of T, Y of T. Right? And as you know from the theory, there are exactly n linearly independent functions as the solutions of this equation, and their linear combination stands for the general solution of the homogeneous equation. Okay? Now, we consider a linear homogeneous equation with constant coefficients. And this is the case where all solutions are expressible in terms of elementary functions of mathematical analysis. Okay? We'll see that this is true. Now, Let's write a few equations. Examples are, for example, the ODEs, look, y double prime minus y is 0, or y triple prime plus 2y double prime minus 1 over 2y prime plus pi times y is 0, okay? Or y4 plus y prime plus or minus y is 0 are all equations, homogeneous linear equations with constant coefficient. The first one is a second order ODE, homogeneous linear ODE with constant coefficient. The second one is a third order ODE, homogeneous linear ODE with constant coefficient. And the last one is a fourth order homogeneous ODE with constant coefficients. Okay? So, our objective, which is suggested by the general theory, is to find n linearly independent solutions. Okay? To form first a fundamental set of solutions, and then taking the combination of n independent solutions to generate the general solution of the homogeneous equation under consideration. So it is reasonable to think that, look, an exponential function, look at that, an exponential function like this, y of t e to the power lambda t has derivatives which are expressible in terms of e to the power lambda t itself. Okay? So it is reasonable to think that our differential equation, homogeneous linear differential equation, has a solution which is of exponential type. Good? So look, actually, let us propose so look, let us propose a solution of the type e to the power lambda t. Okay? Well, lambda is a constant. We don't know whether it is real or complex. Real or complex, to be determined. Good? Now, this is our equation, or in operator form, this is our equation. So, if a function is suggested as a solution of a differential equation, to fix ideas, we implicitly say that substitution of that function into the differential equation is possible. That is, it is differentiable up to at least order n. And the direct substitution into the equation satisfies the equation. Okay? So if this is the case, look, our exponential function is clearly differentiable Okay? Up to any order. So let us find its derivatives and substitute into the differential equation and to see whether this function satisfies the differential equation or not. Okay? That is the very simple idea behind our study. Look, so if we say that if y of t or e to power lambda t is a solution, it must satisfy the differential equation. So please be careful when we say differential equation from now on. I mean a linear ODE, homogeneous linear ODE having constant coefficients, right? So if e to power lambda t is a solution of our equation, it must satisfy the equation upon substitution or upon direct substitution. That is, look, y is e to power lambda t. Its derivative is lambda e to power lambda t. Its second derivative is lambda squared e to power lambda t. And its nth derivative is lambda n e to power lambda t. Good? So substitution into the equation. Okay? So we must have lambda to power n e to power lambda t. The next term is a1 lambda n minus 1 e to power lambda t. And a n minus 1 y prime, which is lambda times e to power lambda t. A n y, so a n e to power lambda t must be 0. Okay? I'm not sure if this is the case, but it must be 0 if e to power lambda t is indeed a solution. Okay? So look, every term is proportional to lambda t. So we have e to power lambda t times that lambda n, a1 lambda n minus 1 plus a n minus 1 lambda plus a n must be 0. Okay? This equation must be 0 if e to power lambda t we propose is indeed a solution. Okay? Now, it is interesting to see that the term in braces is nothing but our differential operator. Look. Look at the differential operator, which is regarded as a function of the operator d, formally as a function of operator d. Look, and replace operator d by the number lambda. Okay? We get our differential operator. So this is nothing, the term in braces is nothing but our differential operator where d is replaced by lambda. Good? So we must have e to power lambda. So we must have, for this proposed solution to be indeed a solution, we must have this e to power lambda t, L of lambda must be 0. Good? So an exponential function is never zero. So the second factor should be zero, which implies that L of lambda must be zero to this end. That is, e to power lambda t is a solution. Okay? So e to power lambda t is never zero, or in other words, if e to power lambda t is zero, okay, you can say that y equal to zero. Observe that y equal to zero, y equal to zero is always a solution of the homogeneous equation, which is called trivial solution. So y0 is always a solution, or you can justify this if any function is a solution, then any constant multiple of that solution is also a solution by linearity. Therefore, 0 is always a solution called the trivial solution, but we are interested in finding non-trivial solutions. Therefore, e to power lambda t is non-zero, so L of lambda must be zero in any case. Okay. So L of lambda, look at the structure of L. So look, since L of lambda, L of d is this one, dn, a1, dn minus 1, a n minus 1, d plus a n. We have the algebraic equation of polynomial equation of degree n in lambda, which is this, okay, explicitly lambda n a1 lambda n minus 1 a n minus 1 lambda plus a n is 0. So this is a polynomial equation in lambda. Actually, the left-hand side is a polynomial of degree n in lambda. So this is a polynomial equation which must be 0. In other words, we have to find the roots of this polynomial equation. Good. So if we find lambda satisfying this polynomial equation, okay, then the exponential function with that lambda becomes a solution of the linear homogeneous ODE with constant coefficients. Now, this equation is called characteristic equation of the differential equation. And this is precisely the same equation when you consider the system representation of our nth order ODE. Okay? Recall that we find the characteristic equation by finding the determinant of the matrix A minus lambda identity and equate to 0 to get the characteristic equation. This is the same characteristic equation. Perhaps we illustrate it later in this simple second order case. Okay, so let's introduce the terminology. Here, L of lambda, the polynomial of degree n in lambda, I mean L of lambda, okay? Lambda n dot, finally a n minus 1 lambda plus a n. Is called the characteristic polynomial of the differential operator L of t. Accordingly, the equation L lambda equal to 0. Okay? This is an equation. Of course, an algebraic equation. The equation is called the characteristic equation of the differential equation of the ODE, of course, homogeneous ODE, L of d y equal to 0. Okay? Please be careful. The left-hand side, which is a polynomial of degree n in lambda, is called the characteristic polynomial. It is a polynomial, actually. It is called the characteristic polynomial of the differential operator. And the equation, when we equate the left-hand side to 0, we get an equation. Such an equation is called the characteristic equation of the differential equation L dy equal to 0. Do not forget our differential equation considered now, which is considered now, is a homogeneous linear ODE with constant coefficient. Okay? And we say that if lambda is a number which satisfies the characteristic equation, then y e to the power lambda t, this function becomes a solution of the differential equation.
And this lambda is either real or complex, right?
Yes, maybe real or complex, to be determined, as I said here. So look, let us recall some results of basic linear algebra. Okay? Recall from basic linear algebra that, roughly speaking, if we have a polynomial equation of degree n, we expect n roots. Okay? Totally, n roots are expected to determine. Of course, these roots may be real and single roots, or maybe real or repeated roots, or maybe complex roots, or repeated complex roots. What else? We know that if there is a complex number satisfying the characteristic equation, okay, then the complex conjugate of that number is also a root of this equation, provided that the coefficients are real, right? And we assume a differential operator with all real coefficients. So this means that complex roots appear in pairs. Okay? So generally from linear algebra, basic linear algebra, it is known that the equation L as L lambda equal to 0. That is the characteristic equation. Yes, explicitly written this equation has totally n roots, which is in a nice agreement in our theory. So corresponding to each root, we produce a solution of exponential type. Good? Of course, provided that the roots are distinct. So we generate, okay, n exponential functions corresponding to distinct n real roots. And therefore, we find n linearly independent solutions of the differential equation, which are all exponential types. And it is not difficult to see that exponential functions with different exponents are linearly independent. Okay? But in general, totally has n roots. However, the roots may be real, complex, single, or multiple roots. In general. Okay? What else? Complex roots appear in pairs. What does it mean? If that, say, lambda 1, a plus ib, where I is the complex unit, okay, is a root of L lambda equal to 0, then lambda 2, a minus ib, which is the complex conjugate, okay? Complex conjugate of lambda 1 is also a root. So, such a complex root, complex conjugate roots appear in pairs. So, these are the general remarks which are very well known from the basic linear algebra about the roots of such a polynomial equation of degree n in lambda. So, as you see, in the case of a differential equation, homogeneous differential equation with constant coefficients, a homogeneous equations with constant coefficients, to find the problem of finding the solutions and linearly independent solutions has been reduced to finding the roots of the characteristic equation. When you find the characteristic equation, roots of the characteristic equation, then it is not difficult to generate the n solutions, independent solutions of the equation. Evet,